Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on vector spaces. So vector spaces are things like R2 and R3. They're sets of vectors, and we usually write vector as a column matrix, although all of what I'm about to say works equally well if you write it as a row matrix or in some other way. And over a field means that those entries in the vector come from a field F. We've been using the field of real numbers, but of course we could use the field of rational numbers or complex numbers instead. And for the vector space to exist, we need to define two operations, vector addition and scalar multiplication. And we need that set of vectors to satisfy 10 axioms that are listed on your screen. So the idea here is that a set of vectors forms a vector space if vector addition and scalar multiplication basically works the way we're used to in R2 and R3. So the 10 things there are axioms. So they're basically rules that you don't need to prove whether or not they're true. They're like starting points. We start with these 10 rules, and everything else that we know about vectors and matrices follows from this. So if you have a set of vectors for which any of these 10 rules does not hold, it's not a vector space, and therefore things don't work exactly as they do in, say, R2, R3, the vector spaces that we're used to. So it's good knowing these axioms because we've been taking them for granted in so many questions that we've done. For example, when we were writing, linear combinations of vectors, the answers that we got wouldn't be true if these axioms didn't hold. So we've been taking them for granted in all the work that we've done on matrices and vectors. Now we're just sort of formalizing it and looking what those axioms are. So R1, R2, R3, R4, R5, they're the best examples of vector spaces, but we'll go through some more in a second. So let's just go through these 10 rules and what they're saying. So the first axiom is saying that the vector space is closed under addition. So if you add any two vectors together from the set, then you get another vector in the set. The second one says that vector addition is commutative. The order of addition doesn't matter. The third one says that vector addition is associative. You can put the brackets wherever you want. The fourth one guarantees the existence of a zero vector, which is the additive identity. So when you add a vector to that zero vector, you don't change the original vector. And the fifth one guarantees the existence of an additive inverse. So for every vector, there's another vector you can add to it to get the additive identity, i.e. the zero vector. So those first 5 axioms basically say that the set of vectors forms an abelian group under addition. So axioms 6 to 10 are all to do with scalars. So scalars aren't actually part of the set V, they're part of the set F, which, as I said, is usually the real numbers. So axiom 6 says that if you take any vector in the set and scale it, multiply it by a scalar, you get another vector in the set. Axiom 7 states that scalar multiplication is distributive over vector addition, and Axiom 8 says that scalar multiplication of a vector is distributive over scalar addition. Axiom 9 says that when you scale a vector, that operation is associative. And Axiom 10 guarantees the existence of a special scalar denoted 1, so that when you times that scalar by any vector, you don't change the vector. So all of these scalars, which I've denoted C and D, they come from a field F, so the usual properties of scalar holds, that if you add two scalars, the order doesn't matter. If you multiply together two scalars, the order doesn't matter. That's guaranteed by the fact that F is a field. All right, now we're going to take a quick look at subspaces. So we know that R2, R3, R4, real numbers in any dimension will form a vector space. But are there subsets of R2, R3, R4 that are also vector spaces? And that's the idea of a subspace. It's a subset of a vector space that is itself a vector space. So we saw 10 axioms for a vector space on the previous slide. If we want to check whether a subset is a vector space, we don't need to check all of those 10 axioms because most of them will be induced on any subset. So for example, the 10th axiom on the previous slide was the existence of the scalar 1, so that 1 times u is equal to u. So that is true for any vector in V, so it will be true for any vector in a subset of V. It turns out, however, that there are 3 of those 10 axioms that are not automatically induced on a subspace of the vector space. So the first axiom we need to check to see whether or not a subset of a vector space is a subspace is the existence of the zero vector. So we said on the previous slide that for a set to be a vector space, the zero vector has to be a member of that set. But there's no reason that the zero vector would have to be in any subset of V. So that's why we need to check number 1. So number 2 is just saying that vectors in the subspace are closed under addition. Once again, we know that that's true in V if V is a vector space, but there's no guarantee that any subset of V will have that property. And the third one is saying that the vectors are closed under scalar multiplication. Once again, we know it's true for V, but that isn't automatically true of any subset of V. So that's why we need to check these 3 axioms. So let's look at some examples. So if I just took the set of all vectors that had the form 1 minus a, let's say a plus 1, and 0, would this set here be a subspace of R3? It turns out it would not, because it doesn't satisfy the first axiom. The 0 vector is not of that form. To get the 0 vector, the first entry implies a would need to be 1, but then the second entry, if a equals 1, would not be 0. So the 0 vector is not in that set, so it wouldn't form a subspace. Now we know that R2 is a vector space, right? Turns out any vector space is a subset of itself. So R2 is a subspace of R2. It's not a subspace of R3. The reason is because it's not a subset of V. So R2 and R3 don't share any vectors in common. So R2 is not a subset of R3, but it is a subset of itself. So if you take any vectors from the original vector space, any number of vectors even, I'm just going to take 2 for example, the span of those vectors will form a subspace of the original vector space. So for example, the span of the vectors here, those 2 vectors there, that's actually a subspace of R3. To see that is actually pretty easy. We know the 0 vector will be in that set, in the span, because the span is the set of all linear combinations of these. So you can just take 0 times the first plus 0 times the second and you get the 0 vector. We know that it will be closed under addition because if you take any linear combination of these 2 vectors, you get another linear combination of those 2 vectors. Similarly, if you take a linear combination of these 2 vectors and scale it, you get another linear combination of those 2 vectors. So that's why the span of any number of vectors from a vector space is a subspace. So now we're going to look at 2 important types of subspaces. So let's say we have this matrix here, A. Of course, here A is a square matrix, although what I'm about to say holds equally for non-square matrices. So there's two important subspaces to consider. Column space of A, which is just the span of all the columns of A, so the span of this vector here, this vector here, this vector here, and this vector here. So the span of all those vectors makes up the column space of A. The other important one is the null space of A, which we've previously called the kernel of A. So remember, the kernel of A contains all of the vectors x such that A times x gives the 0 vector. Of course, remember that if there are any two vectors in the kernel of A, then any linear combination of those vectors is also in the kernel of A. So it's easy to see why each of these would form a subspace of Rn, and that's just because each of these can be seen as just the span of some given vectors. And if you take any vectors, any number of vectors from a vector space, their span always forms a subspace, as I just explained. So because A is a 4 by 4 matrix, here in this example, the column space of A and the kernel or null space of A are both subspaces of R4. We digress for a moment to re-examine what a basis is. I know we've been using this and we talked about the definition, but a very interesting point is that in set theory, there's something called Zorn's lemma, which allows you to prove that every single vector space has a basis, and of course that means every subspace, because it's a vector space, has a basis. So a basis is a set of vectors, which I've called B1 to Bn, such that each of those vectors is linearly independent, and the span of those vectors is equal to H, the vector space. So what that means is a set of vectors forms a basis for H if every vector in H can be written as a linear combination of these vectors here, and there are no linear combinations of the vectors in B that are not in H. That's what I mean by them being the same thing. So we can form a basis for the column space of A and the null space of A, because these are both subspaces. So to find a basis for the column space of A, we're sort of going to assume that the matrix is not invertible, because if the matrix is invertible, the columns of A are already linearly independent, and therefore they are the basis of the column space of A. So it turns out that in the matrix above, A is not invertible. So to find a basis for the column space of A, what we need to do is row reduce A and then take the pivot columns of A. They will form the basis we need. So in row reduced echelon form, A looks like this. So remember, pivot entries are the first non-zero entries in each row. And in row reduced echelon form, they will be the only non-zero entries in their column. So this is a pivot and this is a pivot. So the first column is a pivot column because it has a pivot. The second column is a pivot column because it has a pivot. Of course, it doesn't always work out like that. It is possible that if you row reduce the matrix that the pivot columns will be the first and third columns, or the first and the fourth columns. Just the way of the algorithm, we always make the first column a pivot column. So a basis of A is formed by the pivot columns. Now you have to be careful here. It's not this column and this column that forms a basis for the column space of A. It's the original two columns. So these two columns here form a basis of A. So the column space of A is the span of those two vectors there. So any linear combination of those two vectors is in the column space of A. To find a basis for the kernel or the null space of A, what you need to do is row reduce the augmented matrix with another column of zeros, because remember, you're solving the equation AX equals 0. So when you row reduce it, that's just going to have another column of zeros here. So we're treating this like we're solving an equation. So remember, like, the first column is variable x1. That's the first entry of a vector in the null space, and then x2 is the second column, and so on. So here there are two fixed variables and two free variables. So the first row there says that x1 plus 3x3 is equal to 0. So then we have x1 equals negative 3 times x3. Similarly, the second one tells us that x2 has to equal negative 2 times whatever x3 is. The variable x4 is also free. We haven't got any helpful information about it. It can be literally anything we want, because what this is saying is 0 times x4 is equal to 0, and of course that works for any number. So remember, what we do is we write in terms of the free variables. So we can write this as x3, so x1 is negative 3 times x3, x2 is negative 2 times it, x3 is just 1 times itself, and x4 has no relation with x3, so we put a 0 there. But we also need to do the same for x4. So it's got no relation with x1, x2, or x3, but x4 times 1 gives itself. Okay? So that's what our solution looks like, and it turns out that these two vectors here form a basis for the null space of A. Any linear combination of these two vectors, which of course includes the 0 vector, will be in the null space of A. So I've used the word dimension many times throughout this series, but the dimension of a vector space or subspace is just the number of basis vectors that it has. So in our example, the dimension of the subspace, which was the column space of A, is 2, because there are 2 vectors in its basis, and similarly the dimension of the null space of A was also 2. So both of these are subsets of R4 because A was a 4x4 matrix. If A was a 5x5 matrix, they'd be subsets of R5. So dimension here does have the same meaning as it does when you do like area, because if you look at the vectors that are in the column space of A, if you look at all of them and you were to graph them or plot them, they would form a 2-dimensional plane as a subset of R4. Similarly, for the null space of A, they would form a 2-dimensional plane. It's important to note, however, that even though the dimension of both the column space and null space is 2, they're not equal to R2. They're totally different to R2, even though they have the same dimension. So if two vector spaces have the same dimension, that doesn't mean they're equal. So it turns out for R3 you need 3 basis vectors, so the dimension of R3 is 3. The dimension of Rn is n, because that's how many basis vectors you need. So note, it has to follow the definition of basis here. I mean, I could write, heaps of vectors in a subset of R3, but they would only form a basis if they were linearly independent. So it turns out that if the dimension of a vector space is n, then any set of more than n vectors will be linearly dependent, and we'll look at that in the lessons. I want to point out something that's very important and I think very cool. It holds for any matrix. It turns out that the dimension of the column space of A, which is the same as the rank of A, the same as the number of linearly independent columns, if you add that to the dimension of the null space of A, you always get n, where A is an n by n matrix. So here, note 2 plus 2 equals 4. So if you had a 5 by 5 matrix, if the dimension of the column space of A was 1, that would mean there was one linearly independent column, and it would mean that the dimension of the null space would be 4, and there would be 4 basis vectors in the null space of A. So that's a very important rule called the rank nullity theorem. All right, the last thing I'm going to do is just prove something that I think is really cool. So what I'm about to prove is called the unique representation theorem. So let B be a basis for a vector space V, and X is any vector in V. That vector can be written uniquely as a linear combination of the basis vectors. So just before I start, let's look at what we're actually saying here. Well, firstly, notice that bases for any vector space are not unique. We've seen that. For example, in R2, you could have the basis 0, 1, and 1, 0. You could also have the basis 1, 2, and 3, 4. So there are infinitely many ways to write a basis of a vector space. But because of the definition of a basis, any vector in the vector space can be written as a linear combination of basis vectors. Otherwise, that set wouldn't be a basis. So we know that any X can be written as the linear combination of basis vectors, even though the basis vectors can change. Whatever the basis is, you can write any vector as a linear combination of those vectors. What's really cool about this theorem is it shows that you can do this uniquely. If you take any vector in the vector space, there is only one way that you can write it as a linear combination of the basis vectors. What do I mean by write it uniquely as the linear combination of vectors in B? Well, let's look at what that means. So I know that I can write X as a linear combination of basis vectors. That means I can write X as some constant. So here the constant is a scalar from the field, some constant times the first basis vector plus another constant times the second basis vector, and so on, like this. So as I said, each B here is a vector, each C is a scalar. So when I say written uniquely, I mean there is only one choice of the scalars C1, C2, C3, C4. So I know that I can write X as some scalar times the first basis vector plus scalar times the second basis vector, and so on, because as I said, that's the definition of a basis. You have to be able to write any vector in the vector space as the linear combination of the basis vectors, otherwise they're not basis vectors. So let's say that I can write X another way. So that would mean that I could write X as some other constant times the first basis vector plus a different scalar times the second basis vector, and so on. So what I'm going to do now is I'm going to subtract this bottom equation from this top one here. So I'm just going to subtract each sort of part by itself. So X minus X, if you subtract a vector from itself, you always get the 0 vector. So if I minus this from this, I get C1 B1 minus D1 B1, and so on. But I can write that as C1 minus D1 times B1. So I've used actually one of the axioms of vector spaces here. This was actually the 8th axiom, although on the first screen there was a plus between the C and a D, but remember C plus negative D is the same as C minus D. So I can do that for all of them. So when I subtract the bottom from the top, the next one will be C2 minus D2 times the second basis vector, and again, so on and so forth. Cn minus Dn times the last basis vector. Now, because B is a basis, each of its vectors must be linearly independent, otherwise it's not a basis. So remember, by definition of linearly independent, these vectors B1 to Bn are linearly independent if scalars times each of them equals 0 has only the trivial solution. So B1 to Bn are linearly independent if and only if each of these scalars here is equal to 0. So that means we have C1 minus D1 is equal to 0. C2 minus D2 is equal to 0, and so on. Cn minus Dn is equal to 0. And it's a really easy step now. I just have to, add di to each right-hand side of each equation. So this equation here means that C1 must equal D1, and then this means C2 must equal D2, and so on. Cn is equal to Dn. So if I write x in this way as a linear combination of basis vectors, it uses the exact same scalars as the first way. So that proves there is only one way you can write x as a linear combination of basis vectors. So we knew that we could write x as a linear combination of basis vectors, but we just didn't know before this proof that we could do it uniquely. So another fact that I think is really cool, but I won't prove here because I know the video is getting quite long. If the dimension of a vector space is n, it turns out if you take any n linearly independent vectors from the vector space, they will form a basis. So for example, in R3, any three vectors that are linearly independent to each other, they will form a basis. In R8, any 8 vectors that are linearly independent to each other will form a basis for R8. That works for any vector space, and of course that means for any subspace. Alright, sorry about the long video. This has been the luckiest maths teacher in the world. Have a great day.